right, so the next section is functions and procedures, and this will get you a whole bunch of the levels. So chapter 3.7's got a whole bunch of function call, sort of reverse engineering, and this will give you what you need to solve those. So if you recall, when we before we went into conditional jumps and jumps, that there were two ways to change program control flow. The first was the jumps, and the second was the function call. So a function is a unit of code we can call, and it's similar to a jump, except it can return. When that function returns, it can return back to the place where it got called from, basically. One of the things with functions is that it supports passing data as function arguments and passing values back as return values from that function. It's also referred to as a procedure, a method in C++, or a subroutine. So before we can talk about implementing functions, we have to talk about how a stack works. And I'm assuming you guys cover stacks in 162.3, which is not a prerequisite for this class. So I'm covering stacks anyway. So this will be a good prep for those who are about to take 163. So a stack is a region of memory managed with a last in, first out discipline. Okay, and in x86-64, the stack grows from high addresses down to low addresses. So the bottom is up here, and then you grow the stack downward. With the stack, there's a register, %RSP, that is always pointing to the top. And as you put stuff onto the stack, you decrease RSP, and as you pop stuff off of the stack, you increase RSP. Okay? So the top element has the lowest address in this thing. Okay? And this is essential for function calls. So the x86 instructions that allow you to access the stack are the push and the pop. So a push operation with a source operand fetches that operand, decrements the stack pointer, and then puts that source operand there at that address. So in this case, a push quad, and because it's a quad word, I have to decrement RSP by 8, basically 8 bytes. I subtract 8 from RSP, and then I move the argument, the source argument, into what's pointed to by RSP. So this push quad is equivalent to these two instructions. And before push quad was implemented in the x86 architecture, everybody was doing this. And then the Intel designers were like, why don't we make that one instruction? And so that's how we have a push quad instruction.
Is it faster?
And it would be done as, yeah, there's only one instruction to code, and then underneath you can, one instruction fetch, one instruction decode, and then the operation is done in one step. Whereas this is two instructions, so two instruction decodes, or two fetches, two decodes, and two operations. So that's why they built it into a single instruction, the push quad. And again, you see this pattern everywhere in x86. You see these code patterns. They're like, why don't we make that a single instruction? And that is the complex instruction set architecture way. Versus something like ARM, which says, no, just leave it like that. That is fine right there. Okay. So that's a picture of it. Subtract 8, and then put your value there, and then update, yeah. Okay, so the next thing is pop. Pop Q destination reads the top operand of the stack and moves it into the destination, and then updates the stack pointer to point to the value below. So this is the assembly for it. Move what's pointed to at the top of the stack into RAX for PopQ RAX, and then add quad 8 to RSP to move the stack pointer back up. So that's what that operation is doing. All right. So last in is the first that comes off. Yeah. Oops.
So last in, first out.
Last in, first out.
So is that just a series of, these are just function pointers, right?
This is a address pointer. There are no function pointers. I mean, we haven't said there's anything. It could point to a function pointer, but this is just pointing to an address. Is basically what RSP is doing. You can put data in there. Your function arguments are going to be sometimes there. Your local variables might be there. Your return address is definitely going to be there because we haven't talked about that. Your return address will be there. Yeah.
I have kind of a rhetorical question. So, the stack we see here in memory is this, because we learn stacks as like a data concept, not like how it is actually in the chip.
Implemented, yeah.
Yeah. So this is just like a concept, or it's like a data structure itself.
It's the physical implementation of the data structure. Yeah. So because we're at the lowest level, abstractly you could implement stacks any which way.
Okay.
Yes. In fact, you don't care usually as a programmer. You're like, I'll call the stack class, and stack.push, stack.pop. Yeah, you don't know how that stack class is implemented. Yeah, it could be, but this is the way the x86 stack is implemented. It's implemented at the high range of memory, and there are specific instructions that force this thing to grow down. And we'll see next class, actually, the choice of growing the stack downward gave us all the security problems of the 90s and the early 2000s. Just the direction of it actually messed everything up. Like we lost billions because of that choice. Whereas if we could have just changed the direction, and we'll see this. You just changed the direction, and like none of this would have happened. It was just
Why did you just change it now?
Because we backwards compatibility, everything. You built this into hardware now, right? Like it's like you can't change it anymore. Yeah. Yeah. I mean, yeah, and you want to be backwards compatible, yeah.
So how is it? That's all contiguous memory then, right?
Yes.
Then if it's going to have your function arguments, which could have any size of thing, could
Yep.
be an integer, could be a long int, could be a double, could be whatever.
Yep.
How do you know that you're only increasing it by 8?
The compiler is looking at your program, and if you call a function that's got 1,000 arguments, it's got to create space for that, and it's got to create the instructions that will push all of that junk onto the stack. If you have if your local variables are like, if you have like an array of 1 million longs on the stack, you will see it gets allocated there, on that data structure, because it's a function call, right? And so the local variables. So I'll talk about this later. Actually, the local variables of a function call are stored on the stack. So everything related to functions stored on the stack. And if you just happen to have a huge list of parameters or a huge local variable, that gets stored here.
But how does it know to increase it by that 8 instead of the actual size of that function?
So when you write your code, you're saying this is the data type associated with each argument. You cannot compile a C program without specifically saying what the data types of each argument is, so that it exactly can produce the code that says, oh, I have to do a push quad here because you're pushing a long word. Or, oh, you're pushing a character? I can implement that as a single byte. Turns out it actually doesn't do it as a single byte, but it does. But it can determine, based on the code you've written, the x86 that will implement that. Yeah. So that's what the compiler is doing with this. And we'll see examples of this later on. So. All right, so let's get used to this. Here is an example stack. So again, the bottom of the stack is up here. The top of it is here. At the top of this stack is 123. You see the stack pointer is 108, so it's pointing to this element. And then what we're going to do is we're going to do a push quad RAX. So simulate that in your head and think about what the stack should look like after this instruction and what the stack pointer should look like after this instruction. And then I'll give you 15 seconds to show the result. So figure out, after this instruction, a push quad RAX, figure out what the impact on the stack will be, and the impact on the stack pointer. What will the stack and the stack pointer look like after the instruction, given this initial state? right. So what should the stack look like? Oh yeah. Well, that didn't work at all. The answer's there.
Yeah.
No, I got this great animation though, but like, okay, yeah. So, well, you're right. Well, not that though. That doesn't get there. Actually, what is that? Why is that there anyway? All right. Well, the stack pointer is 100, and then 213 gets pushed onto the top. All right. Pop Q RDX. So assuming RDX is 555 to begin with, simulate that. The answer's not there. All right. So now this is the state of your stack. RSP is pointing to this, right? And then you do a pop Q into RDX. So simulate that. I'll give you 10 seconds. Not quite. It's not the initial. It's not this. That's for sure. There's a reason I put 555 there. I should have put 555 both places.
Because it's a 555 timer?
Because it's not 666. All right, so PopQ RDX, hopefully you got this. You take the top of the stack, you move it into this destination, and then you update the stack pointer to point to 108. Now, if you know, none of this gets cleared off. It's still there, right? But you're updating the stack pointer so that you shouldn't be using that location anymore. Yes?
Does that mean that after your program is run, you can actually trace back to the very furthest that program called onto the stack?
Yes, that memory is still there. So if you have a buffer overflow, for example, and you can access memory beyond your buffer, well, that's the wrong direction. But if you have a way of reading memory, you can get the old stack frames. Yeah, so yeah, that's the other direction. Yeah, so if you have a stray reference, you can pull that data off of that stale stack frame, which is unique. So this is the reason something like Rust is being developed, because Rust will completely shut that down. As soon, so if your programming language wants to build in that semantic where it's going to check for references and only allow you a single reference to a memory location at a time, completely get rid of aliasing, then that's an abstraction that will prevent memory corruption, which is the whole point of these new languages. Yeah.
What would, if you push on the stack again?
If you did push quad RAX on this, then what you're going to do is you're going to decrement this, and then you're going to go into RAX, which had 213. Well, it's going to overwrite 213 with 213. Yeah.
So it's not going to add another. It's just going to go back to that.
Yeah. Because as soon as you do the pop, this memory location is junk. Is considered junk, garbage. And so when you do another push, you overwrite that. Yeah, that's the intent.
What happens when you push another 17 bytes onto our stack? It's a 0 byte.
17 bytes.
You start writing your top memory.
Oh yeah. If you write 256 more bytes.
Right.
Yeah. Well, fortunately. No. I didn't want to give you what the stack addresses actually are, because that would, yeah. All right. Okay, so why are we doing this? Why is a last in, first out discipline being used? Well, it turns out that's what we expect in our function calls, right? The last function that gets called is the first one to return, right? So here is a program. Foo calls who, calls am I. You call them in this order, and the way you want to return is in the last called first return order. That's why we have a stack. And that's why the stack is used to store all the stuff related to functions, stored on the stack. Okay. Some terminology. When foo calls who, foo is the caller, and who is the callee. We have to get that terminology right, because when we're going to start talking about these things, it can easily get confusing. Okay, so now let's get to function calls. The hardware provides you a machine instruction to call a function. And so if you have a label, a function name, then the instruction is call that label, and that label will be basically resolved into a virtual memory address. So you load your code somewhere in memory, and you figure out that virtual memory address, and then you can issue this call on that virtual memory address. And what this instruction will do is that it will push the return address on the stack, because you want to eventually return from this call. So the return address is stored on the stack so that eventually you can return. You can use that address to return to.
That's right after the function call. Like you get its return address before the function call, so you know what that function will return to, right?
Yeah, well, I'll show you an animation of this. It's the instruction right after the call that gets pushed onto the stack, is basically it. Because you don't want to re-execute the call. You want to execute the instruction after the call, is basically what we're talking about. And then you just jump to that label. And then at this label, you execute some code, and at the bottom of that code, there is a return instruction. And the return instruction just takes that return address from the stack and pops it into the instruction pointer, or basically jumps to it. So that's how the function call is implemented in assembly. So here is a picture of it. Again, you have the stack pointer at 120 initially. Your instruction pointer is pointing to this call. So here's this call quad, and that's the virtual memory address of the function you want to call, called mult2. And here is the implementation of mult2. And you see mult2 is at 400/550, and then at the bottom, it calls a ret queue. So we're going to simulate this. After this call, you see that this instruction that you want to return to is here, 400/549. So when you issue the call, you push 500/549 onto the stack, and then you update the stack pointer to point to it. So now the return address is at the top of the stack. You replace the instruction pointer with the destination address. And that puts the processor in the mult2 function. It starts executing mult2. And then when it gets to this ret quad, you see the instruction pointer is pointing to this ret quad. The stack pointer is still pointing to this return address. When you issue the ret quad, it's going to pop the top of this stack and return to it. It's going to take this and jump directly to 400/549. So that's what happens. And then, of course, you have to update the stack pointer to move it off the return address. So now you're executing at 400/549, and this is how the stack is being used for function calls. Questions? Yeah.
We have to implement updating the stack pointer, or is that handled by the instruction?
It's handled by the compiler generating the instructions that will do this for you. Right. So this is the compiler saying, hey, I know C has this calling sort of convention. I want to manage the stack in a way to implement the function calling convention. And I know I have call quad, and I have push quad, and I have pop quad, and I have returns. Those are the instructions I'm going to use. But because in your program you have specified in every detail the number of parameters, the function locations, and all of these things, the compiler can actually generate this for you, is the intent. But we're just trying to figure out how it does this in this class. Yeah.
So dynamic memory is discontiguous inside of the actual machine, but is stack memory all
Contiguous.
Contiguous?
The stack is always contiguous.
Even with the virtualized memory space.
It's contiguous in virtual memory.
Okay.
I don't know where it's stored in physical memory, but in virtual memory, it's a contiguous allocation that grows downward. And typically, per operating system, they limit the maximum size of the stack.
Yeah, so you get stack overflow and stuff like that.
That's different. You get memory out of memory errors if you grow this stack. Like if you have a recursive function, that's infinite. Eventually, you'll push a whole bunch of stack frames all the way down, and then you'll reach the operating system limit, and it'll blow up. Yeah. Well, not physically. Not physically. Yeah. You know.
The instruction says call quad. Does that imply there's a call byte and a call long as well? Does that mean anything?
So it's a call quad because now this 64-bit processor can be run in 32-bit mode. You have all those 32-bit binaries that still want to run on 64-bit processors.
Call quad and call long.
Yeah, and the address on a 32-bit machine is 4 bytes, so it'd be like a call long. And then, yeah, because you're in 64. What's it? It's just call, and then call quad. That's because, yeah, it's a quad word. So yeah, that's why it's called quad.
So then those services are stored into EAX, or the registers which were for 32-bit.
Yeah. So if you're in 32-bit mode and you disassemble it, you'll see everything is EAX, EDX.
Because when we run the MetaSDF, we can see some of the registers, and I was wondering, because the book said something about 32, and sometimes I see it uses it.
Yeah, if you have a int, so in your 64-bit code, if you're using an integer, well then it'll use the 32-bit registers for that.
And says, hey, I can
Yeah, because if you use a byte, it'll use the add byte or the move byte instruction. So, but that's different than function pointers and return addresses. This has to be a quad word because you're running in 64-bit mode. Yeah. Is there anything else? Okay. Practice problem. What does this code do? Given what you know about call, pushes, and pops, what do you think? What is the value of RAX after these two instructions? And what would this be useful for? Raise your hand when you got a guess. All right. Oh, you're all right.
Would it call? So it would call the function and then immediately pop off whatever memory was at, or pop off the stack to input it in RAX.
Yeah, but what value would that be? Very specifically. The address. Yeah, the address of itself, like of this instruction, basically. So RAX is actually going. See, when you do call next, the address of this instruction gets pushed onto the stack. And then instead of actually calling a function, you're just you're in the next instruction here because it's basically calling right there, and it's just popping that address right into RAX. Turns out malware likes to do this because it needs to know the memory address that it's being loaded into. That's one of the things it would like to do. So this is if you're able to insert x86 code into a remote process, this would be something that you could insert to figure out, well, where in the memory space am I, sort of thing. So, because it's hard to get the instruction pointer directly, right? There is no move RIP into a register and then printf. Yes.
Sorry, is it virtual?
Virtual address. Yeah, these are virtual addresses.
Yeah, but if you still have that virtual address, then you can get at that.
That's what we're talking about. Virtual addresses is where the exploit would be using. So, okay. All right. So I gave you a little piece of function calls, but there's a little bit more to functions than just calling and returning. In fact, functions implement not only the return address, but local variables, function arguments, and as it turns out, saved register state. So when the caller foo calls who, well, sometimes it doesn't want who to overwrite all of its registers, right? You have a register set, and you're calling into some other code, and maybe you don't want to have to save all your registers off, call who, and then restore them when who returns. And so there is a calling convention that specifies if you're going to change some registers, you have to save it. And so some of these who will save and restore, and other ones foo will have to be responsible for. So those are the 4 things that are stored for each function. And when we call foo, and then foo calls who, this is implemented in what's known as a stack frame. A stack frame consists of these 4 things for each function that gets invoked. And as you're calling functions, when you invoke a function, you create an entire stack frame for that function, and you push it onto the stack. And then when that function returns, you pop that whole frame off of the stack. And then you'll see that there's code to manage the frames, to make sure you can restore the previous frame after you've sort of updated the picture. So I call those breadcrumbs, and we'll see how these breadcrumbs are used to, when ami returns, to restore whose stack frame exactly the way it was before the call to ami. There was a question? Yeah. Yeah. They won't be. Yeah. Yep. They'll be all over the place. Yeah. And part of the frame management is to keep track of the size of this and to keep track of the old value of of where you need to return to in terms of the frame. How do you restore that frame? And all of that information is stored on the stack and managed by the compiler. Okay, so here's a call chain example. You have foo calls who calls ami, and ami is a little bit recursive. Can call itself a couple of times and can return to who and call ami again. And so in C, we allow this. We allow recursive calls, which most languages do. This is a picture of the stack as I go through this call chain to get you the idea of what's going on the stack as you go through this call chain. So there's a register, RBP, which is called the frame pointer. And the thing with the frame pointer, it always points to the bottom of the current frame. And the reason why we have this frame pointer is because all of your function arguments and all of your local variables, you have to be able to get at them deterministically. So the way we do that is to fix the frame pointer, and sometimes we fix the stack pointer, and then we do offsets from them. And that's how we get at our stuff in the frame, is through these 2 registers. So here is foo, and then eventually it hits who. And then who is in green, and because foo called who, you push whose frame onto the stack in green, and you update both the frame pointer and the stack pointer. Now, one of the things that you save is the old frame pointer, because before you entered, the frame pointer was here. Now you've updated the frame pointer, so when you better keep the old frame pointer around on the stack, so that when who is done, you can restore it back to its original. Who calls ami, pushes the ami frame. Ami calls itself, and because it's calling itself, you still need to create a new frame for it. So this is how recursion works. You call itself, but because this is a separate instance of the function call with different state, you have to create a separate frame for it. Ami calls itself again. And then when this ami returns, you shift the frame pointer and the stack pointer off. You pop that frame off. It's actually still there in memory. It's just, it's unused. But all that data that was in ami's frame is still there. It hasn't been zeroed out.
So when it has to be used again, it
overwrites it.
Overwrites.
Yeah. So then when this thing returns, you pop another frame off. When this returns, you pop another one off. And then when who calls the other ami, you create a new stack frame with new sets of local variables, with new function arguments. And you create a new instantiation of ami. And then this thing returns to who. And then who returns to foo. And then you're back to the original stack. Yeah.
All, like you were saying before, all that memory is still there. You're just moving RPD and RSD.
Yeah.
And when you move it back up, you just overwrite it.
Yep. Yep.
What's the point of having separate frame and stack pointers if they're the same thing, just offset?
Because you might have local variables that are different amongst them. So, for example, ami, if you implemented factorial, and then the function parameter that's getting passed to subsequent recursive calls is different. It's off by 1. You need a separate frame to capture that state. So in C, your function calls are reentrant, meaning that They can't have side effects when they're being called from. They can't have state that relies on other invocations of it. So that's why you create a separate instance that's independent for each invocation. Yeah. Any other questions?
Your data set in your frame,
It varies from frame to frame, and and the compiler will say, hey, I need to do a full-blown frame and push it on, or hey, this function is really easy, don't need the frame. And we'll see both of those cases.
And so it's saving old register states too in that, and that's code that we're just not going to really see, and you probably couldn't see that in assembly.
No, you'll see it, which is why I'm going to explain it to you, so that you're like, oh yeah, that's what that is. I think on some of your levels, you might see a push of a register onto the stack, and then at the end of the function, you'll see it being popped. Well, why is it saving that register and none of the other ones? Well, there's a convention that I'll talk about. And it's just a way for the compiler to help generate code, so it's not saving all the registers every single time. Like, if it knows it can avoid certain registers to avoid the saving of registers and the restoring of them, it will. Okay, so now we're going to go specifically into the 64-bit, or the x86-64 stack frame. And this is different than the 32-bit version. But for this class, all we're going to focus on is this thing. So here we are. The caller stack frame is in pink. The callee is in yellow. And the four things that are in a frame are the function arguments, potentially, the return address, the frame pointer, so return address frame pointer is sort of similar, and then saved registers and local variables. So that makes up a frame. In terms of arguments, we have seen already that most of the arguments are passed in registers. We had this discussion, I think, last class. So we use RDI, RSI, RDX, and you've seen this already in some of your assembly code. We typically like to pass parameters in registers because we don't want to push things onto the stack, because that's expensive memory operations. But if I have a function with 1,000 parameters, I don't have 1,000 registers. And so if I have more than 6 integer arguments, then I spill over onto the stack. So arguments are pushed onto the stack if there are more than 7, and that starts with the 7th argument. So the first 6 are passed in registers, and then if I have more than 6, I'll put it on the stack. The other thing that is in this frame is as soon as I push the arguments onto the stack, I issue that call instruction, and the call instruction is going to push the return address onto the stack, and then jump to the yellow, jump to the callee. When you are in the callee has to save the old frame pointer from pink. So you'll see one of the first instructions will be a push quad of RBP. That's what's happening. It's saying whatever's in an RBP, gotta save it. That's what this thing does. And then I can update the RBP. After that, I can update the RBP to be whatever the stack pointer is. Because now the stack pointer is pointing to the bottom of yellow's frame. So those are the first 2 instructions that you'll often see in a function call and you've seen these in the previous assembly examples, is a push quad RBP and then a move quad of RSP into RBP. And that's your whole frame management thing, right? I save the old frame, I update the frame pointer to now point to the bottom, and then I can start doing other stuff.
Now, RPP, is that like a register? Or is that
It's a register, and it's the frame pointer register.
so it's a dedicated one for the frame?
Dedicated one for the frame, just like the stack pointer is a dedicated one for where you are in the stack. Yeah.
They're not really used for anything else in the system?
Yes. And in fact, if you, in your embedded assembly, start messing with RBP, you'll find that your thing will crash, right? You'll try and return, like you'll mess up, it'll try and restore a frame that's pointing to something else, and then you'll blow up your.
Is that how you do like frame injection?
You could, if you're an adversary and you're messing with someone's stack, and then you can mess with the return addresses, frame addresses, all that sort of stuff.
So you said that RBP holds a frame pointer.
RBP is the
Yeah.
frame pointer.
Okay.
This is always going to point to the bottom
But
of the
does
frame.
hold a value as well? Because like in one of the MetaSTF, you had to actually kind of like dereference the RBP, and you might hold a value or it might have an address where you go to.
Oh yeah, so that's so
it's
one
the
of the
same
things
thing.
is when you fix this, now all of your local variables and all your arguments are a fixed offset from RBP, and that's for that level.
Okay.
You were looking, it looks like it's pulling a string from RBP minus hex 34.
Yeah.
Well, I can actually go to that address and be like, oh, well, let me see what the string is, and then that's the password.
Yeah.
And then, that's what's happening.
Okay.
Yeah, in that level. Which level is that? That's like a GDB level, I think.
It's like initial like 330.
GDB intro.
Yeah.
So that's the GDB intro one. It's like, hey, there's something on the stack. It's pointing to your password. Give me the GDB. Just type in the GDB that prints out the password.
Because in my mind, I thought it just was having a value, and it holds an address. It holds an address which points to a value. Actually, that's what I was thinking was. But now,
Yeah, it depends on what's on the stack. So if this is actually a pointer to an array of characters that has the password, then you would have to find the address that's stored there and then follow it and then get the password string. Yeah, I think that's for that level.
Yeah.
Yes. Okay. So one of the things when you're the callee, so you save the old frame pointer. You allocate space for local variables. So if I have an array of 16 integers, I actually have to update the stack pointer to move beyond this to allocate that space so that the function code itself can then use that space for whatever it needs to use it for. And this is if you can't keep those local variables in registers. So if you only have like 1 or 2 local variables, then you don't need to store those on the stack. In fact, you would rather them be kept in registers and to use the registers directly. So sometimes you'll see local variables allocated, sometimes not. And the same thing with registers. If you are going to use registers that the caller is expecting you not to touch, then the yellow guy's got to save them at the beginning, and then at the very end has to restore them. Yeah.
Is the arguments there the same arguments? The arguments from the pink section and the arguments from the yellow
No. Okay. So, and then if the yellow one wants to call another function, then again, it has to do an argument build. If there are more than 7 arguments in the call it's going to make, it has to create its own argument build. Otherwise, it has to put those function arguments in registers and then do the call.
So it only has to save and restore registers and it's going to modify it? Or
Correct. That it modifies and the caller is expecting not to be modified. We'll get to this though.
Is there any way to specify that between functions, or is that just something?
It is a hard-coded convention by the compiler and x86 that these registers are for the caller to use and for the callee not to touch, and then vice versa. There's a set that does the opposite. Okay, so function arguments. The first 6 are passed in these registers, and the mnemonic that the CTF level gives you is Diane's silk dress cost $89. And then that gives you the order of the registers as they're used. And then if you have more than 6, they get pushed onto the stack. So argument 7, 8, all the way to argument n. And then the other thing about the calling convention is that the return value is always an RAX. We saw that already. Okay, so here is swap revisited. And in this case, you don't see any frame management. You do see parameter passing, though. So in this case, you pass the parameter XP and YP in RDI and RSI. And then the move happens, and then a return. So there are no stack operations here other than the call and the return. Okay, so this is the simplest function invocation, and it doesn't have any of that stuff that I just talked about in terms of frame management. So you'll sometimes see that. One of the things is that this thing doesn't call another function. So that's sort of why it doesn't need to allocate a frame for itself, because there's no frame that needs to be placed underneath it. basically. So that's why this is the simplest. This is called a leaf function, where it's not used to call another function.
It's more like one of the conditionals from the case statement we were looking at earlier. Where it has like the case, and then it has the colon, and then it just has the return at the bottom. Where it looks really stupid.
Not quite sure, but yeah.
Or shouldn't it push the contents of the current registers onto the stack, or is that done in the previous?
So here's the thing. There's when I talk about the register saving conventions, RDI and RSI are assumed to be not saved by the callee. So the caller knows that the callee is going to overwrite RDI and RSI. So the caller has to save those if it needs them for the return. But then there's other registers that the caller, in fact, RBX is one of them. RBX and what's the other one? RCX? No. RBX is a register that the callee is not supposed to touch, or not supposed to modify. And then that's where the callee would save it. Yeah, but right now you're using RDI and RSI without saving them because the caller knows you're going to overwrite them, and that's just the calling convention. Okay. So, function arguments beyond 6. So here is an example of a function call foo that has significant amount of local variables, and a call to foo that has a significant number of function parameters. So given this C function is compiled into this assembly code, identify the arguments being passed to foo. Like, where are the arguments? Which line is corresponding to A of 0, for example, of passing A0 into foo? Which one do you think?
It's going to be the one that's the closest, the furthest away from the stack frame, right?
Give me a number. Which one of these instructions is setting up A0 as the first argument to foo? How do you pass arguments?
47. Because it's the 0x RSP. It's the furthest down in the stack list. That's going to be the furthest in the argument list, right?
So the first argument is always passed in RDI. So this is why this has to be A of 0. And A of 0 starts at a low memory address, and then from there, every 8 bytes is the next element of the array. So you see this is A of 0, and then you add 8. This is A of 1, gets put into RSI, which is the second argument. A of 2, A of 3. In fact, so there's A of 0, A of 1, 2, 3, 4, and 5. And so we said that the first 6 arguments are passed in registers. Because we're giving it way more than 6, the rest of it has to get stored on the stack. So that is what these instructions are doing. And you'll note that you're not using push quads and pop quads as I had talked about earlier. What you're actually doing is you're subtracting a whole bunch off of RSP, and then you're directly doing base plus displacement off of RSP to load up the stack for the function calls. So that's basically what's happening. And here, so this is A of 5. It's at hex 48. So A of 6 is at hex 50. So these two instructions move A of 6 into RAX, and then moves RAX to RSP, parentheses RSP. This is putting it at the top of the stack. And then building upwards. So top of the stack, and then the next one in, and the next one in. This is building your function arguments on the stack in order to get to all the way to here. So do you guys see that?
The OX50. So 25 would be A6.
Yep.
1B would be 7. And then so on every 2 lines.
Yeah. So that's what all of this is doing.
No.
And you notice that both the accessing the A, which goes from hex 20 to hex 68, and accessing these function arguments, which goes from hex from hex 0 RSP all the way to hex 18 RSP, you see that they're just constant offsets from the stack pointer. You're subtracting A8 from the stack pointer, and then you're building both the array here. You're allocating space for both the array and these arguments at the end that are beyond 7 or beyond 6. Yeah.
Is there a reason why it's doing the complicated ones first, essentially, and not the easy ones? And it's like reading this as it's actually running this program, right? It starts at 0 and goes to 7, C, right, all the way down. So is there a reason why it's going and doing those first, other than assuming that you're maybe you have more time early on?
Yeah, I don't know. Good question. In fact, I would be able to argue the opposite. The reason why this would be the first one, because sequential access, increasing sequential access makes sense to me, and it makes sense when we get to chapter 6. Reverse access, going from the end back. Yeah.
Assuming that you have more time or you have less time complexity at the very first part of the function, so that you can spend more time on it compared to later.
I don't know.
Does this mean that it was going to have faster access time given the values of our first 6 data numbers?
Yes. Because then it has to pull these from the stack. Yeah, it has to go into memory. Yeah. So, and this is a nice optimization, because how many function calls have you written that have more than 6 parameters? Not many, right? So that's a reasonable thing to do.
So if we put our most used parameters towards the beginning of our list of parameters, it's going to increase our proficiency in the poly function.
You should probably minimize the number of parameters to the essential, and then you would make sure you are passing as registers. Yeah, that's what I would do. Okay, so local variables, we just saw 2 different ways of handling local variables. In the swap case, they were all kept in registers, but in this case, they had to be allocated on the stack because you had way too many integers, long integers, to store in registers. Okay? So basically what happens is that the compiler, if it needs to allocate space on the stack for the local variables, we call this register spilling, where you don't have enough space in the registers to handle the local variables. The compiler allocates that space and then updates RSP and then allows your code to use those memory locations to store the temporary variables. When the current function calls another function, you have to preserve all of those local variables, right? You don't want the subsequent stack frame to overwrite the local variables. So it's up to the compiler to make sure that the stack pointer is updated beyond the local variables before it's allowed to call. And that's what this code is doing. This thing is making room for both A16 and these parameters in the function build before calling foo, so that foo doesn't overwrite all of that stuff. So that's basically it. Okay. And you'll see that A8 is both this plus that. The math is approximately correct. Given some padding that the compiler can sometimes put in there, it's correct.
We're passing by reference and just have to back up the value.
Yeah, okay, so if you don't want to actually pass all of these, so we say it's passed by value, because you're actually giving it each individual element of this array. If you just wanted to pass by reference, you could just say foo of A, and then it would pass the pointer to A, and then it would be a single argument in RDI that would get passed. Because if you use the literal by itself, you're actually using the address of the first element, basically as the pointer. So that would be an efficient way of passing A rather than doing all this mess, basically.
This has to compute more space, like if it's just the address of the first pointer. That's what makes it efficient.
Yeah, but then like inside, so actually it's the same. So inside of foo, then rather than just operating on these parameters directly, you have to index into the array, the pointer array that you've been given to get the elements. Yeah.
Well, more and more it starts to make sense.
Okay.
Like passing the reference and the value.
Yeah.
Like why they are and what they do.
So now that I've given you this, the level to do right after class is 3.7 param stack and 3.7 params registers. Because on one of them, the pointer to the password is in your registers, and the other one, the pointer to the password is somewhere in the stack. So those two levels are doable now for you guys. And it would just be a matter of, in the debugger, finding the thing that you suspect is a pointer to that thing, and then just doing an x/s on it and see. And by now, you see that most of the passwords have a pretty unique sequence of characters. You can figure out what a password looks like. To enter that in. Okay, there are some issues with local variables. One deals with scoping. So typically, when this function returns, all of the variables that are scoped inside of it are no longer in scope. They're supposed to be completely obliterated. The problem with C is that C allows you all sorts of references and aliases to data that, even though should no longer be valid, you have a valid handle to. That's a problem. And this code is an example of this. I have a function, takes a parameter x, it's got a local variable n, a local pointer to an integer np. I set the local variable to x, I set the np pointer to the address of n, and this is pointing to this variable. It's an alias to n, and then I return np. Well, here's the thing. np is pointing to an integer that now has gone out of scope. That's bad news. You can still use after free, basically, is that bug. And if you Google use after free, you see like Firefox hates it, Google Chrome, like all these pieces of software, they hate that because that leads to memory corruption, which leads to game over to most applications. So one of the things that a programming language like Rust will do is say, no, there can only be one alias. And as soon as the ownership gets passed to this other guy, it gets deleted. It gets whacked. All the references. You're not allowed to have that. Well, for certain cases, I should say. All right. So if you pass this pointer back and you return, then when you dereference that pointer outside, it might actually still work. It'll still give you data, but it's whatever is at that location. And so you can. Here's an example here. I won't go through it, where you have an invalid reference that's being allowed. Okay. Wow, that animation's broken.
Would that be a serious security flaw?
It is. It is, yes. Which is sort of why it's on here, because these are things that are easy to write in C. So that's why you have to. Yeah. All right.
So how would you exploit that? Would you just like allocate the memory, change the value of the deallocate the memory as a race condition before that has to get like a new process?
Make a character array or something like that.
Trying to imagine.
Because if your memory manager has it allocated to your process, you have to free that before it was able to be read without causing
Right. You would have to, or if it maps into a local variable on a subsequent function call, that would, because when you call a function, it doesn't initialize all the stack locations to 0 necessarily for the local variables. So if you have an uninitialized local variable, you'll pick up the previous, potentially previous. But it's hard to say the scenario that would lead to ownage on that. But that's typically, when you see something like that, that's where ownage happens, yeah.
Couldn't you do something like allocate a character array that's going to be larger than register will be, and then you could actually know that your memory is outside of your memory space and outside of registers, and then after you free it, the compiler thinks it's whatever, and you can still read it and say, oh, could be whatever data I might want, and store that somewhere else.
Yeah, so on the spot, I won't be able to come up with the example, but yeah, something to think about. Okay, I want to go through, I don't need to go through that one. Oh, maybe I should. Let me see if I'm... Okay, I will go through this example just because I think this is actually just to recap this whole calling convention thing. Here we have an increment function. Takes a pointer and a value, does some local operations, and then returns a value. This is how it's implemented. And you can see here, RDI is a pointer, and you dereference that pointer and load it into RAX. That's what this instruction is. Then you add RAX to RSI. That's what this RSI is val. RAX has X in it. And so that's RSI is now a Y. And then you move Y into star P, which is parentheses RDI. So this assembly code, and because this is such a simple function, you see that there's no frame management going on. Okay. And then we have a outer call. So this is the caller. And so the caller has these two long variables, v1 and v2. It sets v1 to 15213, and then it calls increment with the address of v1 and 3000, and it sets the return value to v2 and then returns v1 plus v2. And so this is the assembly code that we're going to reverse engineer that implements this call increment. We'll start with this stack pointer here. Return address. This return address is the return address that call incr goes to. And so we'll go through the instructions in red. And on the right is the stack structure that gets updated after you execute the instructions in red. So here, subtract quad $16 RSP. This is allocating space on the stack for your two local variables, right? So you have two long integers. Those are both 8 bytes. So the caller, so we're going to call incr the caller, has to make room on the stack frame for both integers so that it can actually call incr and then have those variables remain intact. So that's what the first subtract does. And then it moves 15213 into 8 RSP, and this is your local variable, right? You subtract 16 off of that, and then at the top of the stack you have v2, and then at 8 above you have v1. So that's with those two variables, and that's why you're using 8 RSP. So you're not really using a frame pointer here as well. You're just directly offsetting from the stack pointer. And then you move 3000 into ESI, and that's your second parameter. Remember Diane's silk dress? So that is the silk part, so that's argument number 2, which is 300. And then this will load the address of v1 into RDI, so 8 RSP, which is the address of v1. And then you load that address into RDI. Those are your two parameters. And then you can call increment with those two parameters. And then at the end, you do this add quad of 8 RSP into RAX. That is this. So what was in RAX before? Well, this is going to be, let me see. Where was RAX? RAX is the return value for increment. We said that the function puts its return in RAX, so this is v2. So RAX had v2, which was the return value of increment, and then I'm going to add v1 to it. So v1 is at 8 RSP, and that's my return value because I do a return of v1 plus v2, and then I restore the frame. I have to update the frame again so that the stack pointer points to the return address. If I didn't do this and I did the return, I'll return to nowhere, or basically random. So I have to restore the stack the way I had it before, and then I can return directly back at the location. And actually, I explained all of that, and I skipped the animation, which is unfortunate because...
And the 8 RSP recipe is calculated by the compiler.
Generated by the compiler at compile time because it knows it's managing the stack pointer.
Doing all the math.
It's doing all the math. Yeah. So, okay. So that's the animation. I just explained it verbally, so hopefully that works. Okay. So let's talk about register saving conventions. So we already talked about it briefly. Can a register be used for temporary storage by the callee? So for example, foo is using RDX, it calls who, and who is sitting here using RDX as well. So what determines whether or not a callee can use a register given to it by the caller? It turns out there is a convention that gets established by the compiler, and there are two sets of registers. There are the caller save, that the caller, if it wants to keep the values in those registers, has to save first before calling the callee. And then there's another set where the callee has to save those registers if it wants to use them. And so here are the caller saved registers. These are registers that the caller assumes the callee is going to overwrite. So if it needs anything out of these registers to be saved, it has to save it itself before calling. So RAX, all the parameters, the function arguments, you assume that the callee is going to consume those and modify them. And then R10 and R11. So this is the return value. These are the function arguments. And then R10 and R11 are other registers that the callee can use with impunity. Okay. The other ones are callee save. So these are the registers that if the callee wants to use, it has to save those on the stack somewhere. It has to push those onto the stack, including the frame pointer if it needs to use it. And we saw earlier that sometimes, like it's not often that the frame pointer gets used now, because what the compiler will try and do is avoid having to save that frame pointer. And it's a memory operation, so it tries to avoid doing that if it can. Okay. Oh, that's what it is color-coded?
Can I take it?
Sure. Yeah, I wouldn't memorize this necessarily. I would always refer to this if I needed it. But I would remember Diane's silk dress cost $89, and those are pretty much all that and RAX are pretty much all the scratch registers for the callee, and then pretty much anything else you think about saving them.
Yeah. Is there one stack on the system, or is there?
There's one stack. Okay.
Virtualized process.
For a process, there's one process stack, but for a threaded application, there are multiple stacks. There's a stack per thread. That you'll get in operating systems. But yeah, if you have a multi-threaded application, you guys haven't had threads or... Okay, so that's a preview. You can have a program that's got multiple contexts executing, and they swap amongst each other, and they synchronize amongst each other. They would have separate stacks, each one of them.
But is it the same back in this? I remember when the first Pentium came out and they were like advertising them like multiple threading and stuff. It's the same thing?
Hyperthreading
I
hyperthreading is different.
Okay.
Really quick jumps, right?
Hyperthreading, so in a context switch, you have to save all of these, right? That's painful. So what happens if I have a shadow set of registers?
So
And I just switch from one bank to the other? That's hyperthreading.
And they're physical registers? Those?
Yeah.
So they have twice the registers, and the way it shifts so quickly is just having a core for each. Or not a core.
Switching. Having a bit that says, use that one, or use that one. Yeah, shadow registers. Yeah, and I think ARM has this as well.
So you theoretically bank like 4 times hyperthreading, 8 times.
Yes.
So it's
Yes.
paging register tables. That was the-
Paging register
Okay,
tables.
so like, there's an old concept of like memory paging, where you could like have one pointer, like point to several different pages of memory, you could change that pointer, and the hardware would look at different pages of memory. So you could only look at one page at a time. This is like under 8-bit addressing, if you want to go into 64K memory. So if you have multiple, you said there's a shadow.
Like shadow
So
registers,
you
yeah.
have a bit that you set, so it looks at the
Yeah, and then you can take it a step further with sort of hardware virtualization. You can have more stuff virtualized and multiple versions of it, and that's where you get some benefits architecturally. And this will be, when you get into the operating systems class, I hope this is part of that. I'm assuming it's part of that class. Okay, so here is an example of a callee saved register. So again, you when you get into call linker, if you're using RBX, then you have to push it. And then you do a subtract quad to allocate the frame, the two long words. And then you have your code. And then at the very end, you restore the frame. You add your 16 to it. So get beyond the local, deallocate the local variables. And then you do a pop quad of RBX if RBX is being used. So this is something you might see in your compiled code. I haven't checked if it's in your binaries at all. I would imagine not, because my code is the levels are simple enough that it would probably not need to use RBX. But that's what it's doing. Okay, up until this point, we have not talked about floating point arguments. But as it turns out, floating point arguments use a completely different register set. So if you pass floats or doubles as parameters, they won't go into RDI, RSI, RDX, or those registers. They'll get passed in these registers. And just like we have AX, EAX, and RAX, for these registers, we have XMM0, YMM0, and ZMM0. These are vectored floating point registers. And because a lot of our multimedia and a lot of our scientific computations are single instruction, multiple data, we have these really wide registers for floating point, and these can be used for vectored integer operations as well. So we typically will pass floating point operands now using these registers. And this is something unique to x86-64. It used to be that floating point arguments got passed in a different register set that's now deprecated. This is for x86-64 that we're using these XMM registers for. And in fact, we're not using the entire XMM register. We're using either the bottom half of it for a double or the bottom quarter of it if you have a float. And that is where your parameters are passed, and then the return value is also passed in these registers. Okay.
What does it mean to vectored registers?
Meaning rather than passing one double, I can pass 16 doubles. Yeah, and then I can have an instruction that rather than give me one floating point operation, it can give me 16. And so there are different code words for this. There's MMX was the first one for Intel, and then there was SSE, and then there was AVX, and now there's AVX 512. This will, I think, some of you might have processors that are this one, and then you would be able to do the homework. You'd be able to get a 40 times speed improvement if you have the AVX hardware. Then, but actually, don't do the AVX because we have to run it, and we don't have an AVX 512 machine. But, yeah, the labs here are AVX 256, and that's what we're running it on. So actually, only do the instructions that we tell you to use. But if you do have your own, and you know that you have that, you can actually use the next one up. You can actually use the DMM instruction. Yeah.
Why don't we have like a standard virtual machine which everybody can run so that everybody's operating?
This is a hardware thing. So you can't issue these AVX 512 instructions in the VM. It'll basically fail. It'll be an illegal instruction because it needs the underlying hardware. Yes, yeah. So it's not that vector operation isn't implemented. It'll just throw an error. Well, I don't know what kind of error, but it wouldn't work. Yeah.
Could you simulate it as two smaller registers or something?
You could. So there's Transmeta was this company that Linus Torvalds was a part of for a while that was using binary translation to take something like this and say, I don't have that instruction. I'll on the fly change the programming of the processor. Yeah, the performance is terrible.
But
when you get that. Apparently, it would basically do like a bunch of RISC operations to emulate the complex instruction. So all right. We'll talk more about this when we get to the performance, the SIMD lecture, actually. So that's why I'm just going to skip over this right now. Here is the assembly code of this function, swap element. Explain the jump. So in our up until this point, we say, oh yeah, you call this function swap element does its thing, and there should be a return here. Why is this being implemented as a jump? Jump to swap. Best guess. Yeah.
Swap's really returning an integer that signals what the result was. Like a 1 or 0, if it worked, or 0 if it didn't.
It is or it isn't returning?
It is returning.
It is returning something that does what?
That an integer usually it's like a 1 if it worked, or 0 if it didn't.
So in this case, it's the return is void. Oh, this swap.
But
You're not using, that's part of it. So you're not using the return value of swap. What else is there? That's part of it.
Swap is a leaf function.
That's the other one. It's a leaf function. So after you call into swap, swap is going to return. And if you did this as a call swap, and then swap runs, and you call return, it's going to go back here and call another return. Double return. And it's like, why did I do that? Why don't I just do a jump? And then when the swap function returns, it'll skip over this, and it goes directly to whatever called swap element. That's the key. And because you're not consuming the return value of swap, you can do this. And because swap is the exact last thing that executes in this function, you're going to say, I don't need to return to swap LE anymore. As soon as I go into swap, have swap return directly to the caller. I skip a node in the graph, basically.
But if you were using swap value to say print it out or something, it would...
Then you have to use the return. Yeah.
So your swap does the return?
So yeah, your swap, this function will return, and then rather than returning to this guy, which will just do another return because it's the leaf, it's just that I'm going to skip that return, and I'm just going to implement this as a jump.
That's kind of cool. That's really cool.
Yeah, and then this will throw you, this will throw you for a loop until you realize, okay, that pattern is there because of this.
Well, compiler optimization sometimes just takes swap and get it right there, not even have another.
So we'll talk about this in chapter 5. The compiler cannot go into functions and do optimizations between functions. It usually doesn't. It's just an intractable problem for it. So usually the optimizations stop at a function call. Yeah.
So does that mean a new stack frame doesn't have to be created?
A stack frame does get created for swap.
Only if swap calls a stack frame information.
No. I take that back. You're right. There is no stack frame that gets created for swap. It's basically going to use swap. It's going to tack on to swap elements frame, basically.
Part of that function.
Yeah, you're right. That's correct. So there is no return address in there, for example. Eventually, there might be an allocation. So a local variable allocation or a saved register allocation might be there. So in a sense, it's actually just tacking that on to swap elements frame, technically.
Doesn't that make it a little bit unsafe? Because the whole point of having the local variable and reallocating the stack frame is to say this is the maximum that I can go. And then if you're making a local variable inside of this essentially extended stack frame, doesn't that create some possible issues?
Well, the compiler is generating this code very tightly in the offsets, so yeah, I don't think so offhand, but yeah. I've been proven wrong before, so.
But it's not really creating a frame for swap because
That's correct. It's basically tacking on
it's treating it as if it was a part
a swap element, so that when it returns, it's really returning on swap elements frame, not its own, because it didn't create one, basically. That's what it's doing.
So then the frame pointer would be moved to the bottom of the new extension?
frame. So this one doesn't have a frame pointer, but if jump swap does have a frame pointer, it would be taking the frame pointer from the caller to swap element and saving that. So when the return happens, it's going to return to the caller, and you're fine because that's what you wanted.
Yeah. So like the frame for the swap element, would that be extended over the swap and call that?
Yeah, effectively that's what's happening.
Quick question. So the caller is main? Like how I tried to.
It could be main. Yeah.
It could be main.
Yeah.
Okay.
The swap has to implement its different scope. Will it be?
Yes.
It'll create a frame at that point. Or?
Yeah, and it'll create the local variables, and it'll create those sorts of things.
Okay.
And you sort of have a little bit of it here. At least the registers are passing parameters. So when you call the jump, the parameters are set up in the registers, and then it will allocate its own local variables. So really, it is sort of merged frames, I would say. And it's merged because there is no return address that gets. All right. I think I'm done anyway.
If we were to inline the function, then it would compile so that it wouldn't even need to jump. It would also use one function. Like we inline swap into our source code.
Yeah, and then it wouldn't need the jump at all. Yeah, if you inlined it. Yeah. Okay. I want to quickly cover this. There are a whole bunch of different calling conventions out there. There's in 32-bit land, there's the cdecl, there's the standard call, and then when they realized that the memory issues were difficult, then there was this fast call that was implemented. There was a Microsoft version of it. There was a Linux version of it. And so this is a mess when you have a bunch of binary code compiled with different calling conventions. So now in Visual Studio and in GCC, if you want to use a library that's got a different calling convention, there are ways to declare that in your program. And that's what I want you to take away from this. Not all programs are compiled with the calling convention I just showed you. Okay. There's even a C++ calling convention. So in C++, you have the magic this variable. For those of you who had C++, the way that gets implemented is it gets passed into ECX or RCX. So different languages have different calling conventions. So there's that.
What this does?
What's
This, I mean the